Okay, hi, thank you. Today I'm going to show you our research on industrial control systems. But before I start, I would like to give a short introduction about who we are. I work at OpenSource Security, and we are mainly focused on Linux security. But a few years ago, we started to pen test embedded devices and related technology. For example, RFID systems. In addition, we do research on industrial control systems, and that is the reason why I'm here today. Our research on this topic was motivated by the Stuxnet worm. The Stuxnet was a worm that was able to attack Siemens PLCs, and it used bugs in Windows to spread. And that means the worm requires Windows to spread. And starting from this assumption, we were wondering if it's possible to create a PLC worm that is able to spread over PLCs without any external hard or software support. And the answer is yes, that it is possible. But before I show you how we did this, I give you some background information on the devices we chose. We chose an S7 1200 PLC. It is a small PLC. It is built for small application. It has 40 kilobyte of RAM and nearly 1 megabyte of persistent memory, so it's a really small device. All the different submodels of this S12700 have a built-in Ethernet port, and we looked at it in firmware version 3 and in the TIA portal at version 11. The TIA portal is a software that is used by an engineer to program these PLCs. Compared to a usual computer, these systems work differently. It works in cycles. Each cycle will start with reading the inputs, writing the outputs, and after that, the user program is executed. The user program is a piece of software that is created by the engineer, and it controls the actual machine. For example, a traffic light or whatever machine you want to control. After that, there are other tasks taking place. For example, the communication with other devices. And if one cycle ends, the next starts. And there's an upper limit for each upper time limit for each cycle. This is called the cycle time, and on Siemens PLCs, that is usually 150 milliseconds. And if one cycle takes more time, the PLC will report an error and stops the execution. The user program is structured in so-called program blocks or program organization blocks. There are basically 6 different types of program blocks. The first is called organization block. It can be seen as the entry point of the program. There are function blocks. Function blocks are comparable to classes known from object-oriented programming languages, for example, Java. We have functions. Functions are usual functions known from C, for example. And we have the system ones, system function blocks, system function that are provided by the vendor. So they are some kind of library you can use. In the end, we have a data block. A data block is some kind of global memory, and it allows you to store any data in it and access it from everywhere in your PLC program. These program blocks can be programmed in different programming languages. We have graphical ones, for example. Here's a ladder diagram, the function block diagram. These kind of programming languages are used by electricians, for example. These people are familiar with these kind of diagrams. There are also text-based programming languages, for example, structured text, and we chose this for our work. Okay, if you want to implement a worm, what are the different parts you have to implement? The first thing you need to do is to implement a target discovery, because the worm needs to find its targets on its own. After that, you need a way to copy yourself onto the target system, because the worm needs to copy itself. After that, the copy needs to be activated, to be executed on the target system, and in the end, an attacker wants to have some kind of payload to do some evil stuff. And now I show you how we implemented the 4 different parts step by step. I will start with the target discovery. If you want to implement a target discovery, the first thing you need is a characteristic that allows you to identify Siemens PLCs. And every Siemens PLC has an open TCP port 102. The port is always open, the user cannot close the port, and that means if you found an open port 102 on your network, the probability is high that you found a Siemens PLC. And our basic idea here was to implement a port scanner in the programming language of the PLC. We have 2 system function blocks that helped us with this task. The first is called tcon, it opens a new TCP connection, and there's a tdiscon, it closes a TCP connection. On this slide you can see the implementation. There are a lot of, you can see the call of the tcon call here in the upper corner. There are a lot of parameters that are passed to the function, but the most important are the IP address and the port you want to connect to. After the first call of the tcon function, the function is processed in background by the firmware. And in the next cycle, we come back to this part of the code and call the function again. But this time we can ask the firmware, is the connection setup already done? If yes, we found a new target and can continue with the infection. If not, we have a little problem because the firmware will try to connect endlessly to the target system and the target system is maybe not there. So we need to implement a timeout by ourselves. We simply count the cycles in which we fail to establish a new connection, and if we hit an upper limit, we switch to this part of the code, and here you can see the tdiscon call. We simply call it. It will fail because it tells us you trying to close a connection that was never established, but it frees the resources for the next connection attempt. And here in the bottom corner, we simply increment the last byte of a 4-byte IP address, and that means we scan in /24 subnet for an open port 102. And this is the target discovery. The next point is the carrier mechanism. Usually, new programs are transferred via TCP onto the PLC. And our basic idea here was to implement this transfer protocol with the help of the PLC programming language. We have again 2 functions, tsend, treceive. They allow us to send any TCP data, so we are able to implement this protocol. The problem here is to understand the protocol that is used to transfer new programs to a PLC. It is called S7COM+. It is a binary protocol, and there's no public documentation available on how this protocol is working. It has huge difference compared to the old S7 300, 400 protocols, and it allows us to do a lot of things. For example, you can start the CPU, you can stop the CPU, you can change the outputs, and in addition, you can transfer programs onto the PLC and back from the PLC to the engineering station. Now, I show you what we found out about this protocol, reserved this protocol. What you can see on this slide is the first message. The first message is sent from the TIA portal, so the engineering software, to the PLC. In the case it wants to establish a new connection. And like every message, this message has a basic layout. It starts with a byte 72 always. Then we have a version field, a length field, which tells us how many data is transferred. We have a type field, which tells us something about the intention of the message, for example, request, error, response. We have a reserved field. We have a subtype, which tells us something more about the intention of the message. And there's a sequence number. And in the end, we see a frame end delimiter, and if this frame end delimiter is missing, it simply means that the frame is fragmented and is continued in the next frame. But if you look at this slide, you will see there are a lot of more bytes between the message head and the frame end delimiter. And in the beginning, we had some problems to find any structure here. But if you look close enough, you see a lot of A3 bytes. And we found out that A3 bytes introduce a so-called attribute block. Attribute blocks structure the data that is actually transferred between the PLC and the TIA portal. In this case, some kind of server session ID. Like the whole message, each attribute block has a basic layout. You can see the layout on this slide. After the A3 bytes, there's an ID field, which tells us which value is transferred. There's a field which is usually 0, maybe some kind of format. We have a data type. In this case, it is a string. A string has an additional length field, and in the end, the actual value that we want to transfer is placed. In the beginning, we had some problems to pass this attribute correctly because the number encoding is a little bit strange. You can see two numbers in this example. The first is the ID field, and the second is the length field. And if a number starts with a 1 bit, it means there's an additional byte following, which also belongs to the number. For example, this ID field starts with a 1, so there's an additional byte field. In contrast to that, we have the length field starts with a 0, so there's no following byte. After we understood this, we were able to pass these messages correctly. On this slide, you can see the next message. The next message is the second message, and it's a replay from the PLC, and it basically says, "Hi, I'm a PLC, and I want to talk to you too." And we are only interested in the red framed byte here because this is an anti-replay protection. If you simply record all messages and replay it, it will fail because the PLC will not accept this message because of this protection. What you have to do is you need to record this byte and flip the first bit. And the result needs to be placed in every message you send from this point on to the PLC. For example, here, the third message completes the connection setup. Then there's another message which is interesting for our work. It's a Programtransfer message. It has the same structure as I mentioned before, but there are two new interesting fields in the message head. The first is the block type. It defines which type of block we want to transfer, for example, a data block, a function block, so the ones I mentioned before. And there's a block number. The block number is the place where the block is stored on the PLC. After that, there are a lot of attribute blocks following, and some of the values that transferred in these attribute blocks are only used by the TIA portal. For example, the source code is always stored on the PLC because you can receive the program back out of the PLC into your engineering station. And there are other informations, for example, the bytecode that is actually executed by the PLC that is only used by the PLC. There are a lot of more informations, for example, the time of the last modification, a lot of more informations. Okay, at this point we knew a lot about the protocol. We knew how to set up a new connection, how to overcome the anti-replay protection, how to calculate length fields correctly, and we are able to create own program transfer messages. Then the next step we had to do was to implement everything with the help of the tsend and treceive functions. The messages that we need to send are stored in data blocks. And finally, we created a tool that allows us to inject the first PLC with the worm. Okay. That is a carrier mechanism. The next thing is that we need to activate the copy that we transferred to the target system. And this part is very easy because it is a built-in feature. As I mentioned before, the organization program block is some kind of program entry. And what you need to know is that on Siemens PLCs, you can have more than one program entry point. And so we simply implement the worm as organization block, transfer to the PLC, and the PLC will start the execution of our code. In addition, we do not touch the original user program. It's completely untouched. We only add new parts. So easy part built in. In the end, you want to have some payloads, and you are part of the normal user program now, and that means you can do whatever a user program can do. You can change the outputs to values you like. You have the TCP functions. You can implement a command and control server, a proxy server, whatever you like. Okay, and so we implemented all 4 different parts. And the next thing I will show is a little demo video. What you will see is that an attacker will infect the first PLC, then the worm will spread over the other PLCs, and in the end, the PLCs will connect to a command and control server, which is under control of the attacker. Okay, here we have the movie. Now it's playing, okay. You can see 4 different PLCs back in my lab in Germany. Each PLC controls a different part of the little demo factory, and as you can see, everything is working normally. It produces little yellow pieces, and everything is good. And on the right side, you can see the attacker screen. The attacker will start a command and control server in a few seconds. Now the last piece is produced. So now I plug off 3 PLCs because I want to prevent the worm from spreading too fast. I want to infect the first PLC, and then I connect the PLCs back. So now the attacker starts the command and control server. So it is running, and the next step is that the attacker will infect the first PLC. That is done by our own Python script, and you can see it will take only a few seconds. Now the infection is in progress, and maybe 10 seconds later, it is done, and the first PLC is infected. So you can see it is already connected to the command and control server, and now I plug in the 3 other PLCs. The worm scans for these PLCs, and what you can see is that during this process, the factory works normally. But there's a short moment in time, it's right now, when the infection is in process, the original user program is stopped. You can improve that, but this is not implemented currently in our worm. And you see the infection of the second PLC is done, and it is connected to the command and control server. And now this part of the factory is working normally again. So now I think the infection of the third PLC is in progress, and all four PLCs are connected right now. Yes, you see everything is working normally. The next thing we can do is that we control the PLCs with the help of our command and control server. So the PLCs connected out of the industrial control network to us, and we are able to send commands to these PLCs. For example, we can change the outputs to values we like. You can see here the slider is moving, but there is no yellow piece. We can start the assembly lines, for example here, and we can also start the second assembly line. And we can do whatever we want. We can set everything, so I stop everything, now it's stopped. We can set everything to random values if we like. So now the fabric is out of control. And if this is a real factory, your factory could be broken now. In this case, it's also broken. I have to fix it, but it is very easy. So I put in a little yellow thing again. And now it's not moving, but you see, in this case, it's very easy. It's fixed. I guess the second slider is also broken. It's not working. But in a few seconds, it's also fixed. Okay, now the factory is working normally again. The next thing I want to show you is that we implemented a proxy server. So we are able to use this connection, the PLC created to our command and control server, and we are able to use this connection to get back into the industrial control network, and we can or can set up any TCP or UDP connection we want. In this example, I'm doing a port scan of one PLC with the help of the other PLCs. You can see it on the right side. Now the scan is in progress, and I think Nmap will scan the 1,000 most common ports now. By the way, the setup is here. It's down in the Geek Lounge, and if you want to see it later, how it is working more hands-on, you can come to me, ask me questions. I will be in the Geek Lounge after this talk. Okay, the scan is in progress. You see the factory is still working normally. Everything is working. Yes, and I think the scan is finished in a few seconds. Now, so there's the result. Port 80 and port 443 are open. That means there's a web server running on the PLC. Okay, the last thing I want to show you is the kill function. The kill function allows us to shut down the factory by simply typing kill. You see it in a few seconds. Right now, see everything is blinking here. All PLCs disconnected, and an engineer has to reset the device by device to get the factory working again. Okay, that was the demo part. Now back to the slides. Now the question is, what is the impact on the PLC? We saw that the program execution is stopped for approximately 10 seconds, and this generates a log entry in the PLC. You are able to recognize that something strange is going on. But you can improve that because you can patch existing programs. This Siemens feature. You can patch it online, and the PLC will, without any interruption, execute new code. This will make the worm more complex, so it is not implemented yet. The worm uses memory, in this case nearly 40 kilobytes of RAM and 220 kilobytes of persistent memories, and that is small enough to fit in all the different models. And the cycle time is important, because if we take more than 150 milliseconds for our execution, the PLC will stop the execution of the worm. The longest cycle we could measure was 7 milliseconds, and that matches our assumptions, because most of the time we use communications functions which are processed in background by the firmware. The worm is part of the normal user program, so it will survive a cold restart. If you want to remove the worm, you can do a factory reset that will delete the whole user program, including the worm, or you can overwrite the program block that is used for the worm. The next question is how you can protect yourself against these worms. Siemens PLCs provide 3 different protection mechanisms, and the first is called Knowhow Protection. Knowhow Protection is basically a password protection, and it allows you to prevent unauthorized readings or modifications of the code. The protection is implemented by a attribute block, which is transferred between the TIA portal and the PLC. In case you transfer a new program, you can see this attribute block here, and it is basically here, you can see it's an enable flag. If this flag is 1, it means this protection is activated. And now if you, in addition, there's a SHA-1 hash of the password you choose. If you want to disable it, what have you to do? Simply flip the bit to 0, and it is disabled. You can transfer the program back with your own tool, and the TI portal will see, oh, it's disabled, and will not ask for the password. Problem here is the source code is still AES encrypted, but the question is, how is the AES key generated? And the AES key is calculated from the hash we saw a few slides ago. To make this point clear, you can always ask the PLC, I want to have your program, please. And you will get the whole program, including the attribute block, which is used for the protection, and this block contains the hash. So, and here you can see how you calculate the key for the encryption. Just take the hash, truncate it to 128-bit, and XOR it with M. And M is a static value and displayed on this slide. So this means you can always calculate the key by asking the PLC for the key. This is fixed in the newest version of the TIA portal, but here the Knowhow protection is broken, and it only protects existing programs. But our worm adds new parts of the program, so this is an ineffective protection against worms. The next is called copy protection. The copy protection allows you to bind your program to a specific PLC. You can enter the serial number, and if you try to download the program to a different PLC, the TIA portal will say, oh, it's the wrong serial number, you're not allowed to do this. The problem here is it's a client-side protection, and only the TIA portal will check the serial number. And if you have your own tool, you can choose whatever serial number you like, and the PLC will accept the program. So it's broken, and again, it only protects the program that is already stored on the PLC. There's the last protection, it's called the access protection. the access protection does not protect the program, but it protects or it limits the features of the protocol, of the program transfer protocol, that can you use without providing a password. You have three different protections levels here. The first is off. You can do everything, but there's a second level. It's called the write protection, and if this write protection is enabled, you are not able to transfer new programs onto the PLC. The problem here is it works, but it is disabled by default. So this means we do not need to or overcome any protection in the default settings. So it's some kind of Morris worm from 1988 we heard before. Then we looked at other PLC vendors because we were interested if this is a Siemens-specific problem or if other PLC vendors also affected. And we need three basic features. The first was industrial Ethernet. We need to connect to these PLCs. The second feature is that we need to transfer new programs onto the PLC via TCP. And in the end, we need programmable TCP functions to implement the protocol that is used for program transfers. And on this slide, you can see a list of leading vendors. You can see Siemens, Rockwell Automation, Schneider, Mitsubishi Electric, for example. And there's only one PLC which has no TCP function today. And if you also cut out these who are not able to or have no programmable TCP functions, you have still a lot of left. And for example, Rockwell Automation and Mitsubishi Electric, and this shows us that this is not a Siemens-specific problem, so but that all PLCs can infected with malware, and I think we have no good tools to check what is going on our PLCs, and maybe we need to change this. And it's the end of my talk. Thank you.
Thank you very much. Well, you must have fun at work.
Yes.
So, if we start on this side, the question to the audience was, would your organization be able to detect infected ICS equipment? And what is your opinion on that? Is it even possible? I think most people don't think so.
I think it is possible to detect this because what is happening here is that one PLC transfers a program to another PLCs, and this is a strange behavior. Usually you expect the engineering station to do such operations. But the problem here is that you need to understand the protocol, because the protocol is used for changing the outputs, and that is a usual feature which the PLCs do to each other. And so you have to look deep in the protocols and understand what is this message exactly doing, and then you can recognize things like this. But
okay, so it's possible, but it will take some time.
Yeah.
So did you get any reactions from Siemens?
Yes, the reaction was it's very interesting, and everything works as expected, and that is true. Everything works as expected. Right.
Okay. Oh, okay. So they have to do some exercise about their, bounty program, for instance. Do they have any?
I don't know. They say there are professionals in the companies and they need to activate the protection. That is their point.
Okay. Well, that wouldn't be easy. So the next question, what's the name of the toy producer? Not Siemens. I suppose that is for the factory part. So to be looking closer at that, they will go down to the Geek Lunch. You have a live demo down there during the coffee break. Don't miss that, okay?
Okay.
And can you make a version that does not stop the PLC work process when infecting?
Yes, I think I mentioned this already. So you can improve this by patching the online program. The problem here is that you first need to download the existing program into the already infected PLC. Then you need to patch this program, and then you can push it back to the new through the target system. It's a little bit complicated, but it is possible. And then you are not able to recognize that there's something going on by just looking at the systems.
Okay. Mm-hmm. Well, thank you very much. There were some of the questions that I just let you ask if there's a PCAP or if it's on GitHub or whatever. You had sort of funny figures here for later, since you will be able to meet Maik downstairs. And as a token, again, and a very big thank you for your work and effort in this area and for your presentation. Thank you very much.